Hello, everybody. It's Mrs. Pound, and we are starting a new chapter today, chapter 26 on sound. But remember, chapter 25 on vibrations and waves laid a lot of groundwork for this chapter that we still have to know in order to talk about sound. So, our objectives today are going to be to relate the pitch of a sound to frequency, describe what happens to air when sound waves move through it, and compare the transmission of sound through air with transmission through solids, liquids, and a vacuum. So, section 26.1 in the book is about the origin of sound. The first thing we want to talk about is pitch. This is the term that refers to how high or low sound frequencies appear. A higher frequency means a higher pitch, and therefore also a lower frequency is a lower pitch. And I have here two tuning forks in the background. They have different frequencies written on them, and so they have different pitches. Sometimes in music, you'll also hear a lot of talk about octaves. And an octave is 8 notes, therefore oct, 8, like octagon, octopus, okay? And octogenarian, somebody who's 80 years old. So 1, 2, 3, 4, 5, 6, 7, 8 keys, that's an octave. And the cool thing about octaves is that if you know the frequency of one note, say like A 440, you know the frequency of the A above it and the A below it. The A above it will be A 80 hertz, and the A below it will be 220 hertz. So music actually is very mathematical and has a lot to do with physics. Now, if a sound is infrasonic, that means it's below 20 hertz, and that means humans cannot hear it. However, we have found that animals such as elephants can actually produce sounds below our hearing level that we cannot hear. That's why I have a picture of an elephant there. There are also ultrasonic sounds, those sounds that are above 20,000 hertz. And this is a picture of a dog whistle, because when you blow a dog whistle, you cannot hear it because it's above 20,000 hertz, but your dog can. So human hearing range is between 20 and 20,000 hertz. And remember, the source of all sounds, just like the source of all waves, is vibration. So for instance, if you start the strings on this guitar vibrating, you will hear a sound. Now let's talk about sounds in the air. Sounds produce in the air compressions. This is a pulse of compressed air. And so I have this picture here to show that these peppercorns are all bunched up. They are compressed together. There are also rarefactions. This is a disturbance in air in which the pressure is lowered. So these peppercorns are spread out, just like the molecules in air would be for a compression versus a rarefaction. So the peppercorns represent air molecules. Now, remember, sound waves are longitudinal. So they are parallel to the medium, the way they are moving, like a slinky. When we compress it, here's the compression, here's the rarefaction. So when listening to Mozart, the pulse travels across the room, not the medium or the air, just like the slinky. Think about the slinky. It's compressed here and it's rarefied, I guess you would say, here. But it's not that these coils took the place of these coils. It's the pulse that passed through them. The pulse caused this compression, it caused this rarefaction, but the coils themselves are moving a little bit, but they're not moving across the room. They're staying relatively in place, compressing, and then moving on to the next, the pulse is moving on to the next bit of air, compressing that, and so on. The air does not actually pass across the room. So when you are hearing somebody, it's not that the air has traveled all the way from their mouth to your ear. The pulse has compressed and rarefied the air until it hits your ear. So sound waves in air are a series of, number one, high and low pressure regions. So here is a high pressure region, here is a low pressure region. Periodic condensations and rarefactions. So a condensation, a rarefaction, and they happen periodically, predictably, okay, across the room. And they are also, we could say, periodic disturbances. So add these labels to the picture, or draw this picture, in your notes. You could simplify it a bit. But this is your area of high pressure, your condensation. This is your area of low pressure, your rarefaction. So add that to your notes. Now, media that transmit sound. The first thing we need to know is that sound waves cannot travel in a vacuum. I'm going to show you a video on this in class in which we take the air out of a bell jar and we're going to see what happens. But sound cannot travel in a vacuum. Therefore, if you're in outer space and you were talking to somebody, it would not travel to them if you could do that. That's why we have to use radios with radio signals, because those can travel in a vacuum, and we'll talk about that when we talk about light. Now, states of matter in order from worst transmitter of sound to the best transmitter of sound. Just take a second and think, which do you think is the worst and best transmitter of sound? Thinking of solids, liquids, and gases. If you said that gas is the worst transmitter and solids are the best transmitter, you are correct. Gases are the worst, then liquids, and solids are the best. It's because of the spacing between the molecules. In a solid, the molecules are very close, so they can hit each other and transmit that sound the best. Gas is actually the worst, and actually you'll find that if you're like in a swimming pool, you will hear sounds better in the water than you will in the air. And you know that being in a swimming pool, you can still hear sound. And likewise in a solid, if you put your head down on your desk and you tap on it, it will be louder than if your ear is above the desk. So which of the following would be most likely to transmit sound the best? Water in a swimming pool, water in the ocean, air in your classroom, or steel in a bridge? The answer would be steel in a bridge because it's the solid. Now let's take a look at the rest of them. The air in your classroom would be the worst, but what about water in a swimming pool and water in the ocean? That's a little more difficult, but water in a swimming pool would be worse than water in the ocean. Water in the ocean has a lot of dissolved minerals that fill in some of those spaces, and so sound would travel slightly better in water in the ocean. Now let's talk about wave speed. The speed of sound is 330 meters per second in dry air at 0 degrees Celsius. Why do I set those stipulations of dry air, 0 degrees Celsius? The reason is because the speed of sound can change depending on what it's traveling through. So is it in an air, a gas, or is it in a solid? And it can also vary with the temperature. So the speed of sound is not always the same. It does vary, but it is 330 meters per second in dry air at 0 degrees Celsius. Compared to the speed of light, it is 1/1,000,000th the speed of light. It's much slower, and you know this if you have ever seen a flash of lightning. You know that you see the lightning before you hear it, and you can roughly calculate the distance to the lightning based on that time lapse between when you hear it and when you see it. And so it is much slower. Now let's talk about loudness, because some of us like to listen to our music really loud and it's not good for our ears. The unit for intensity of sound is the decibel. It's named after Alexander Graham Bell, and it is a logarithmic scale. What that means is that it does not go up in a nice straight line, that if you have a loudness here and you double the decibels, it's just doubling it. No, it is a scale like this, where it goes up more by like a value of 10 each time. So the difference between 0 and 1 decibel is not the same as between, say, it does not multiply equally as going from, say, 0 to 2. It just doesn't double. It actually goes up a lot more. So when they say like the decibels are doubled, that means it's actually the loudness has gone up quite a bit more than just doubling. So that can be very dangerous for your ears. So our objectives today were to relate the pitch of a sound to frequency, describe what happens to air when sound moves through it, and compare the transmission of sound through air with transmission through solids, liquids, and a vacuum. Now in class, we're going to continue these discussions, and I'm going to clarify a lot of these things with demonstrations and some selected videos that we're going to watch to really firm up these concepts in your mind. So don't forget your 5 questions, and I'll be back with more about sound.